Hello everyone, today we're going to have a look at Cartesian equations and coordinates, and also coordinates in 3 dimensions. So just like in 2 dimensions, we can have equations of lines and spheres and other shapes in 3 dimensions. Now of course, as we've seen before, we can also express points in 3 dimensions. These points represent the position of a point in R cubed space. R cubed, or real cubed space, just means 3D space. And we can express these points in the form x, y, and z as we've seen. So points in this 3-dimensional space look something like this. Our first example, we want to show that these points are collinear. Now there's many different ways to show points are collinear, and I'm going to show you a way that we haven't done in the past. We've done it other ways, and I'm going to show you an alternate way. So one way of showing points are collinear is by finding the magnitude of each of these points. Now if we find the magnitude of AB, which is the square root of 2 minus 1 squared, plus minus 4 minus 1 squared, so minus 4 plus 1 squared, plus 5 minus 3 squared, you get the square root of 14. Now if we do that the same for the magnitude of BC, we get the magnitude of vector BC is 3 root 14. And if we do the same process for AC, we get 4 root 14. So what we've just done is we've found the magnitude of the entire line from A to C, and we've also found the magnitude of intervals within that line, so BC and AB. So these points are collinear as the sum of AB and BC is equal to the magnitude of AC, the sum of the magnitudes, I should say. And since they have a point B in common, then they have to be collinear if their magnitudes are adding up to give that larger value. Now part C says using vectors show that ABC is a straight line. To do that, we're just going to find AB. Now AB is just going to be B minus A. So 2 minus 1, we get 1, minus 4 plus 1, minus 3, and then 2. Let's find BC. BC, we're going C minus B, or OC minus OB. That gets us 5 minus 2 is 3. And then we get minus 9 and 6. Then we think, okay, for points to be collinear, these points must be some magnitude of the other point. That means they have the same direction. So this is 3 lots of the top vector. So we know that these vectors have the same direction. Does that make it a straight line? Not all of the time, but in this case it will, because they have point B as a common point. So if I'm a line, or if I'm 2 lines and I've got a common point and I've got the same direction, my angle with the angle theta is the same, then they have to be collinear, a straight line. Okay, an equation of a sphere. So in 2 dimensions, the equation of a circle is given by x minus a squared plus y minus b squared equals r squared. And a circle is defined as a set of points, the locus, on a plane equidistant from a fixed point, which is the centre of a circle. Now in a similar way, a sphere is defined as a set of points in 3 dimensions, equidistant from a fixed point in 3 dimensions. Now if our point is x, y, z, is a point in space, and point C, H, K, L is a fixed point in space, then the distance between the centre and C is going to be x minus h squared plus y minus k squared plus z minus l squared, all square rooted, using the distance formula. Now, our definition of the distance of PC is going to be the same because we're defining PC to be a fixed point from the centre. So no matter where it is, it has to be the same distance by the definition we chose. So we're going to call PC the radius of the sphere, which means the radius is equal to that. Now if we square both sides, we're going to get this is the equation of a sphere. So this is my equation of a sphere with radius r and centre HKL. Okay. So we need to show that this equation is the equation of a sphere and find the coordinates of its centre and radius. Here we're going to complete the square 3 times. Again, who would never think you would need to use completing the square in the real world? Here we're using it right now. So we're going to complete the square on the x, y and z values individually. So I'm going to rewrite this as x squared plus 6x plus y squared minus 4y plus z squared plus 2z. And I'm going to make it equal to minus 6 by moving everything over. Now what I'm going to do as well is I'm going to leave some gaps because I'm going to complete the square. So if we complete the square, divide 6 by 2 and square it, we get plus 9. Divide the 4 by 2 and square it, we get plus 4. Divide the 2 by 2 and square it, we get 1. And then we're plussing 9 plus 4 is 13 plus 14. Okay, so here we've got a sphere, x plus 3 squared by doing a perfect square factorization, y minus 2 squared plus z plus 1 squared, and that's equal to minus 6 plus 14, which is 8. So therefore, this is a sphere with centre minus 3, 2, minus 1, and radius the square root of 8, which is 2 root 2. Okay. Our next example says the spheres x squared plus y squared plus z squared equals 9 and x squared plus y squared plus z minus 4 squared intersect. Find the value of z when they intersect. Well, we know from this equation, if I were to, say, subtract these equations, I would get some things that are cancelling out. So let's go x squared plus y squared plus z squared equals 9. And then on the bottom I've got x squared plus y squared plus z minus 4 squared equals 16. Call that equation 1, and we'll call this equation 2. We have a go at going equation 2 minus equation 1. The x squareds and the y squareds will die. So we're going to have z minus 4 squared minus z squared equals 16 minus 9 is 7. So if we expand all of that, what we should get, z squareds will cancel, we're going to have plus 8z, so we're going to have 8z, and then we're going to have I might do that, it's too many steps in one I'm trying to do. So we've got z squared minus 8z plus 16 minus z squared equals 7. Yep. And then if we rearrange that, we're going to get 8z equals 9. So z is equal to 9 on 8. So therefore, when z is equal to 9 on 8, they intersect. Part B says, find the equation of the circle in which they intersect. So if two spheres intersect, if they come and intersect with each other, apart from the fact that they might just touch at one point, there might be like a tangent point if you think in calculus, but if they intersect and they kind of go inside of each other, the point of intersection has to be a sphere. So to do that, all we have to do is substitute 9 on 8 into either equation of the circle. So x squared plus y squared, it's going to be easier to substitute it into the equals 9 one, so 9 on 8 squared is 81 on 64 is equal to 9. Giving coordinates of the centre and radius of the circle. So subtracting that over, we get x squared plus y squared equals 495 on 64. So therefore it has a centre of 0, 0, and the value of z we know is 9 on 8. We've been told that in the question. That's its centre. And of course its radius is just going to be the square root of 495 on 64, which if you type that into calculator you get 3 root 55 on 8. Alright, thank you for listening.